Okay, welcome everyone to our second brown bag, no brown bags in here, but brown bag seminar of the fall series. We're going to have two nice presentations today, both coming from people who've worked in the propulsion combustion group area. Jonathan is our first speaker. He is a fifth-year undergraduate student. He's in the BS/MS honors program, and he has worked, and the work he's going to talk about today was done with Professor Steinberg. He's also done research with Professor Shankar in the CFD group. And outside of his technical activities, he's also president of the tour guides, Georgia Tech Tour Guides, the authoritative voice you were using earlier, and a member of the marching band and the jazz ensemble. And I'll let Jonathan talk about what he's going to talk about. Thank you, Jonathan.
Thank you, Dr. Seitzman, for the introduction. Thank you to everyone who showed up in person today and for everyone who's hopped on the call as well. Today, I'm going to be speaking on some of the research I did with Dr. Steinberg in the combustion lab as we were working to convert the Georgia Tech hypersonic capabilities from the shock tube to the shock tunnel a couple falls ago. To give a brief agenda for my presentation, just a little bit of background on the project as a whole. Then we're going to talk about some of the initial nozzle design and then get into the CFD analysis I did verifying that nozzle design. Finally, getting into some CFD verification and results. I'll share some final thoughts from the work and then have time to open the floor for questions as well. So the overall project, the research effort is led by Dr. Steinberg with co-investigators of Dr. Sun and Dr. Walker as well. It's experimental characterization of the wake behind a cylinder body at Mach 5 to Mach 6. The overall objective of the project is to demonstrate the capability to study surface ablation and the thermochemical state of wake behind bodies at hypersonic velocities, and to do this, convert the Georgia Tech high-pressure shock tube to a shock tunnel capable of replicating these Mach 5 to Mach 6 conditions. My work was during the first 2 semesters that this project was going on, so really laying the groundwork in the initial nozzle design and initially transforming the shock tube to the shock tunnel. And this presentation is really going to focus on the first bit of that work with the initial nozzle design. The necessary modifications for the project as a whole were removing the end cap from the shock tube and then designing and attaching a nozzle and a vacuum chamber with a test section to the end of the shock tube at that point. You can see the figure over on the right-hand side of the screen there gives a bit of an image of the end of the shock tube with the nozzle and the corresponding test section and vacuum chamber at the end of it. And as I mentioned, my work can be focused on the initial nozzle design and the CFD process used to verify it. So the actual geometry of the nozzle itself, this work was handled by Anish Shenoy. He was the graduate student at the time that was really leading this effort. And it was me and him working on the project. The nozzle, it was an axi-symmetric design done through the method of characteristics. It was used by fitting a cubic pressure line distribution along the centerline axis. As you can see, we've got a figure here down at the bottom of the page, which is displaying the 100-line axi-symmetric method of characteristics contour plot he used to actually develop it. The geometry itself was based on the capabilities of the pressures achievable both in the shock tube and pressures we would be able to get downstream with the vacuum chamber itself. Overall, looking for a pressure ratio of 529.1 and an R over R star ratio of 5. So as I mentioned, we fit the nozzle contour to that polynomial with an R squared value of 0.9999. And then we got the resulting geometry. Because of constraints with the actual physical geometry of the shock tube and whatnot, we settled on a throat radius of 0.25 inches and an overall test section diameter of 2.5 inches. And this will be a little more relevant later, but the throat location being 0.02 meters downstream of the beginning of the converging section of the nozzle. So where my work really came in was actually using CFD to validate this geometry selection. A lot of the geometry itself was developed using some MATLAB code that we had taken from a student at another university, and we're using their work, and we weren't really sure about the accuracy and the applicability of the code because it was used for supersonic versus what we were doing was hypersonic. So we wanted to look at CFD and use that to make sure that the code itself was something that would be applicable to our project and that we could continue using in the future. So that's where this work comes in. For the CFD work itself, all of it was done using commercial off-the-shelf software. For gridding, I was using Pointwise and for all of the actual problem specification analysis, post-processing and results, all of that was done using ANSYS Fluent, mainly due to the fact that when I began this research, I had not even taken a thermofluids class as an undergraduate, let alone jet and rocket propulsion or anything like that. And Fluent was the easiest software to, one, get my hands on, and then I enrolled in some other courses through Cornell and some other universities separately, and that was the software they were mainly using to teach CFD analysis through those courses. So that was the main reason for choosing ANSYS Fluent for this analysis. As far as the assumptions, the big one was a no-slip wall contour along the actual walls of the nozzle itself. The geometry, as I mentioned, was the axi-symmetric CD nozzle that Anish developed the geometry for. The boundary conditions, we were looking for a pressure ratio of 529.1. So at the reservoir or of the shock tube and the inlet of the nozzle, we were operating at a pressure of 59.21 atm, and then the outlet pressure down in the vacuum tank was going to be 0.1 atm, reservoir temperature of 1300 Kelvin, and the vacuum temperature of around 300 Kelvin. And then finally, the last real thing was actually not using a difference between reference pressure as far as gauge and absolute and stuff like that. I found through reading a lot of papers that for hypersonic, supersonic CFD and ANSYS Fluent, it behaves a lot better and you get much nicer converged results typically when you use a reference or operating pressure of 0 instead of actually dealing with the gauge values and whatnot. The overall solver settings involved the use of the energy equation, and then I ran 2 separate cases. One initial InVisid case, mainly for use of studying my grid and stuff like that, and initial verification of the solution, and then a turbulent case as well, using the one equation SA model. Once again, the choice to use the SA model was based on other papers that I was able to find from similar research experiments at other universities and other places in industry. They found that when doing hypersonic analysis on nozzles, the one equation SA model generally gives better results than, for example, the K epsilon or the K omega 2 equation models and whatnot. The overall expected analysis outcomes were sonic conditions at the throat, as you'd expect from CD nozzle theory, approximately Mach 5 flow at the outlet, ideally uniform flow at the outlet, and then for the turbulent case being run with the SA model, we would expect to see some boundary layer formation along the actual wall of the nozzle. The mesh used, as I mentioned, I developed in Pointwise. It was a 2D structured grid with a boundary condition for a symmetry line going down the middle of the geometry itself. This grid, the one I ended up using for the final analysis, had 12,000 cells in it. For looking at boundary layer prediction and whatnot off of the wall, I used an initial Y plus value of 1, and then from there use a growth factor of 1.2 all the way from the wall down to the axis of the nozzle itself. So right here we have some of the residual plots from the InVisid case and the turbulent case. Overall, a lot of what I found when actually doing the research to do this research was that generally good practice with ANSYS Fluent is setting residuals to converge to a value of 1 e to the negative 6 or lower. So that was the residual criteria I set when doing this analysis. As you can see for the InVisid case, all of the residuals converge to below 1 e to the negative 6 in about 14,500 iterations. For the turbulent case, not all of the residuals got below 1 e to the negative 6. Some of them did, but a lot of them got around 1 e to the negative 4 and stood there. But there was less than 0.5% change in any of these residuals over the last 15,000 iterations. So seeing good convergence in that behavior as well, even though it didn't get quite down to the values I'd set for the residual convergence criteria. To begin validation, the first thing I wanted to look at was kind of a grid refinement study. I mean, a lot of times in CFD, you like to do wind tunnel testing or something like that, but that wasn't something we had the capabilities to do. And as with all CFD, the results are only as valid as what you can prove in other ways. You can't just assume it's all correct. So the first thing was a grid refinement study, mainly focused on using the InVisid case. So what I did is I took my grid that I used for the final runs, and then I made a version of it that was much more coarse. So it had about 75% of the cell density near the wall and about 75% of the total cell count. And so I ran the exact same case as well, and with both the coarse grid and the fine grid to compare behavior around them and make sure that there wasn't any extreme differences between one grid to the other. As you can see on the figure on the right, that's looking at the wall Mach number specifically on, I believe, yeah, it's the wall Mach number specifically. And there was really good behavior and similarities between the fine grid and the coarse grid along the entire length of the nozzle. As you look at the axis Mach number, particularly from about x equals 0.2 meters up to x equals 0.2 meters, there's really good behavior and correspondence between those grids as well. There's a little bit of iffy dipping going on there in the fine grid, but then after about x equals 0.3 meters through the rest of the nozzle as well, you do see good matching as well. So that was nice to see that the grids weren't drastically affecting the results we were seeing with the CFD. The next thing was actually comparing the fluent results to an analytical 1D solution. So I developed a MATLAB script basically that went in and it took the actual geometric coordinates of the nozzle itself, then found the area ratio, and then used the area ratio to solve for Mach number using standard CD nozzle equations for a 1D solution there. So then I then plotted that for the entire length of the nozzle based on the area ratio of the entire geometry, and then compared it to the fluent results. So on the left, we have a comparison of the fluent values to the analytical values for the inviscid case. As you can see, when you start out for the inviscid case, the wall Mach number is lower than the 1D solution, and the axis Mach number is slightly higher than the 1D solution up until the throat location, at which point they all come to Mach 1, and then after that the trend reverses. So you have the axis values being generally higher than the 1D solution and the wall values being generally lower. This was a behavior that was also observed in several papers I read that were working with nozzles that were either supersonic or hypersonic and more similar to this one. It's a trend they were getting in their results as well, which is good to see. And then for the turbulent case, of course, on the wall with the boundary layer formation, you can't really compare that to the analytical 1D solution. But along the axis itself, it does follow a similar trend, particularly to the axis behavior for the inviscid case as well. They follow very similar patterns along the length of the nozzle. So getting on to results, the first thing we have here is a contour plot of Mach number for the inviscid case. The first big thing to notice is that in the nozzle, we do see sonic conditions Mach 1 at the throat, which is what we should expect and want to see. At that point, Mach number increases throughout the diverging section of the nozzle until it reaches the exit with a value of approximately Mach 5.1. This was notably higher than the design value of Mach 5, which was our design point. But overall, the contour plot is revealing expected flow behavior for an inviscid simulation of a CD nozzle. Here we have a similar contour plot, also of Mach number, but for the turbulent case as well. As with the inviscid case, we see sonic conditions at the throat of the nozzle once again, and the contour plot this time is revealing boundary layer formation along the nozzle wall up at the top of the contour plot. Once again, we would expect this because we're running a turbulent case versus the inviscid, where you're not solving the right equations to see boundary layer formation and stuff like that. But the exit Mach number, interestingly, is slightly lower than the design point of Mach 5. So the inviscid was at 5.1, the turbulent was at 4.9. They kind of went on either side of our design point of Mach 5 for this nozzle, which was an interesting result to see. Diving into this a little more and actually comparing the exit Mach number, one of the biggest things we wanted to make sure was that if we make this, the nozzle, it doesn't have a large diameter anyways for the test section. So you're already being limited in the size of a body you can place in it to actually test. Your flow field is not that big. And one of our concerns was the possibility of having an enormous boundary layer and losing an extremely and unacceptably large percentage of our flow field. And that way you're just further restricting the size of a body you can actually put in to the flow field for testing and whatnot. And so here we've plotted the variation in the Mach number at the outlet based on Y position. So at the bottom you can see an interesting offset initially, just like we saw with the contour plots of the turbulent case being at about Mach 4.9 and the inviscid case being at about Mach 5.1. For the inviscid case, it remains fairly constant up the entire length of the nozzle going from the axis to the top wall. But the turbulent case, clearly that's not happening here. You can kind of see where the fluent predictions of the boundary layer start to occur. Looking at the actual boundary layer thickness, if you're doing the just assumption of boundary layer is where you have 0.99 of your free stream velocity, and assuming your free stream velocity is your velocity at the axis of the nozzle itself, that leads to a boundary layer thickness of about 0.00812 meters. which in total, when you consider that on both sides of the nozzle and the entire nozzle area, means that you're losing about 12.5% of your total like 1D exit area, or your total flow field diameter there, which is not ideal. However, we can't really say based off of experimental validation if this would actually be the case, to say if this is the actual boundary layer thickness that is occurring within the nozzle itself. Yeah. And to kind of wrap things up and give some conclusions on this work and the final thoughts, one thing is that both results show good consistency across multiple meshes, which was nice to see. Another thing is that the envisaged result, just based on the fact that you can more accurately compare it to things like 1D analytical solutions, it's more strongly validated than the turbulent result itself. And in the future, it would be definitely worth seeing if you could do actual experimentations with different rakes and other measuring devices to possibly go in and study the actual nozzle itself to further validate the turbulent case, things such as the boundary layer thickness and whatnot within it. Another thing is that we felt that both the turbulent and envisaged results still supported the nozzle geometry selection. Though the nozzle was designed for Mach 5 flow, in reality, for the purposes of the experiment, it doesn't need to be necessarily exactly at Mach 5 flow. We want it to be as close as possible, of course, but with the instrumentation we would actually be using to study the flow field and the wake behind the bodies in there, we would be able to know what the actual Mach number was. And so as long as we're getting close, which was the goal, we're happy with that. We weren't seeing anything crazy. The code we were using to actually generate the nozzle geometry was not producing what we would think to be any unexpected or bad results as far as what we were looking for. Another thing is that, as I mentioned, the turbulent result does anticipate losing a decent portion of the uniform flow field and essentially the test section area. Once again, this would be less than ideal, but we couldn't really confirm that until we would look into further validation and whatnot with the simulations and actual experimental results themselves. With that being said, that's all I really have on the CFD portion of the work on this project. First of all, thank you everyone for attending. If you'd like to follow up with me, I have my GOTTEC email address in the PowerPoint. I'd be happy to email back and forth about any of the work. And I'd like to open the floor to questions, possibly speak about other work I did in this project after this or anything like that.
So again, if you're listening online, please feel free to ask questions on chat and I will repeat them. Any questions from the room?
So I was just going to ask, after you kind of left the project, so like where it went?
Yeah, so after this semester, after we got those CFD results and stuff like that, we ended up taking the geometry that was used for this analysis and whatnot and manufactured the nozzle. We then took it and attached it and converted the shock tube into the shock tunnel like the project was seeking to do. We then spent the first part of that semester building out the rest of the experimental setup as well, and began doing test fires of the nozzle using the equipment we had in the combustion lab. Unfortunately, COVID cut that short, and I was sent home and I wasn't allowed to really work on the project for the rest of the semester. But virtually what I was still able to do, another concern we had with the nozzle was possible oblique shock formation and whatnot at the nozzle outlet. And so while I was still virtual, by working with Dan Fries, who was in the combustion lab at the time, and Anish as well, I was able to come up with a Schlieren imaging system to study potential shock formation in the nozzle, which they ended up setting up and using to look at that as well. I then worked in the CFD lab with Dr. Sankar, so I haven't worked on the project in, I guess, maybe like a year and a half now, so I can't speak too much on to where it's at this very moment. Anything?
I've got one for you. So, yeah. Interesting thing when you start thinking about boundary layer development and flow in those nozzles. What did you assume for the inflow to your nozzle?
The inflow to the nozzle itself, like the inlet boundary condition?
Yep.
Yeah. So the way the nozzle was actually set up in the shock tube itself, it was attached, and then to allow the tube to pressurize and then propagate the shock down, which would then feed the high pressure air into the nozzle. The nozzle had a mylar diaphragm that was put between the end of the shock tube and it. So we had the diaphragms that we were actually cutting out and sealing between the nozzle.
I'm asking about the CFD.
Oh, the CFD?
The CFD, what did you assume?
Yeah. Okay. So getting to that, We assumed a pressure of 59 or 52.91 atm and zero initial flow velocity at that point, because we were assuming the nozzle would burst and there would be zero flow at that point, and then instantaneously the velocity would begin to become just from the pressure.
But you're neglecting the sharp corners and things that will be at the front end of that nozzle going from the shock tube into the tunnel, right?
Yeah, so the diameter of the nozzle was like an exact fit to the outlet on the shock tube, but we were neglecting possible interference from the diaphragm bursting. Yeah.
No boundary layer or anything built up. It was a perfect uniform stagnant.
Yes, yes. Anything else in the room? In the chat, maybe?
Nothing else yet on the chat. I guess I had another question.
Yeah.
Did you look at the fluid to try and see if you were getting any kind of waves, any kind of slightly non-isentropic waves in the fluid calculation?
We did. At the time, I honestly did not have the knowledge to really be figuring that kind of stuff out. I've looked around at it some, like afterwards, just like side project for fun, to look at some of that. And there wasn't anything that looked like we would have been getting anything super non-isentropic.
You were clearly getting those little notches where all of a sudden the pressure.
Yeah, right after the.
That's a wave going through.
Yeah.
You didn't take any kind of like vertical or horizontal.
No.
Anything else? Well, thank you again.
Yeah. All right. Thanks again, everybody.
Okay, let's get ready. Ready? I'll introduce you, but come on up anyway. Boy, that's a lot of names. Our next speaker is Aman. He's a senior, currently undergraduate here in Aerospace. He's working, his research advisor is actually a mechanical engineering professor, Dr. New, and I won't talk about his projects because he will, but just on the personal side, he's interested in space exploration, and he wants to further and pursue a career in space exploration and using work to improve the efficiency of engines. Get that right? Right. Thank you, Aman.
Thank you, everybody, for attending my presentation. I'm going to today be talking about the work I've been doing under Dr. Rick New. In essence, our work seeks to develop models that describe the relationship between high cycle fatigue strength of additively manufactured alloy 625 parts with features that can be controlled by varying the process parameters. We hope by the end of this project to acquire data to develop a digital twin material model for facilitating the concurrent design of the geometry and manufacturing process for an injector in a rotating detonation engine for rockets or other hypersonic applications. So that was a lot of big words, but bear with me, and I think by the end of this presentation, you'll have a much better idea about what I'm talking about. So I'd like to start by giving some background information on rotating detonation engines and why they are better than regular engines that we currently have, especially. The information I will present on this slide was not from my research specifically, but I hope it gives you an appreciation of where my work is going. So rotating detonation engines have actually been theorized for decades, but only recently have we begun to see actual prototype designs and tests of these engines. Rotating detonation engines are predicted to be up to 25% more efficient than our current standard rocket engines, which is a tremendous improvement in efficiency that we really just can't achieve with our current engine designs. So you're probably wondering how these engines work and how they can squeeze more performance out of the same mass of propellant. So the key word in this engine cycle is detonation, which is a very specific type of combustion process where the flame front moves faster than the speed of sound in the material that's burned. In this case, the unburned fuel mixture doesn't move out of the way of the incoming flame front, so the flame front becomes a shock wave that we call the detonation. At the detonation wave, the pressure and temperature rises nearly instantaneously. This is different to most current engines that we have, which are deflagration engines, where we have subsonic flame fronts. The key advantage here is detonation combustion generates pressure gain in the system, whereas our current deflagration combustion causes pressure losses.
Can you stop? Apologize for interrupting. Like hearing stop. Take a break. Sorry, everyone, for that. They just couldn't see your slides. You were there. So just feel free to take off everywhere you want. Sorry about that.
No worries. So yeah, anyways, as I said, the key advantage here is detonation combustion generates pressure gain in the system, whereas our current deflagration combustion processes cause pressure losses. So in this study, specifically, the additive
My bad.
my bad. I'd also like to give a quick background, my apologies, on additive manufacturing and the high cycle fatigue and how it all ties into it. So additive manufacturing, also known as 3D printing, utilizes technologies that build three-dimensional objects by adding layers of material. This material can range from plastics, metals, and one day, hopefully, even human tissue. 3D printing techniques have already proven to greatly improve the ease, speed, and costs of manufacturing parts in comparison to a lot of other traditional manufacturing techniques such as casting or forging, etc. In this study specifically, the additive manufacturing process that we used was laser powder bed fusion. This process utilizes a large laser which melts thin layers of powder. Once a layer is solidified, a new powder layer can be spread, and the process is repeated until the part is created. Throughout this process, designers can choose to vary multiple parameters, such as the thickness of layers, laser speed, and hat spacing to design their parts. The nature of this process, however, can also create surface roughness and internal defects, such as porosity, which are typically caused by unfused materials. We aim to learn how these defects can be related to the parameters varied throughout the process and how these correlate to the high cycle. If you're not sure what high cycle fatigue is, it is the process of degradation associated with an applied cyclic load that is sufficient to cause a crack to form, or nucleate, as we like to call it. Typically, this is known to occur at some defect or heterogeneity of the microstructure, and the subsequent growth of the crack will lead to the eventual failure of the component, basically causing it to break. This phenomenon occurs in rotating machines and is one of the most likely causes of component failure, which is why high cycle fatigue is an especially important mechanical property in the applications of rotating detonation. So you can see that if our goal is to 3D print the parts for one of these engines, it's crucial that we have a method for predicting the failure of these materials based on a method of 3D printing. So Inconel, which is the material we test in this study, is a nickel-chromium-based superalloy. Inconel is widely used in many aerospace applications since Inconel alloys are oxidation corrosion resistant. They tend to hold well in extreme environments subjected to very high pressures and temperatures, such as in a jet or rocket engine. And here on the table, we can see the composition of the Inconel powder that was used in all our specimens. So a more detailed motivation of the study is shown on this side. The objective is to establish process, structure, property, performance relationships using machine learning methods, highlighted by the yellow boxes, as we can see in this diagram over here. To achieve this, the first step is to develop a database by creating different test specimens generated by different process parameters. In this case, the process parameters are the different parameters that can be altered in the 3D printing process that I showed you on the previous slide, such as layer thickness, hat spacing, laser velocity, etc. For this study, an experiment was designed, which consisted of manufacturing different bills of fatigue specimens with the objective of collecting data. Then the critical features and attributes that control the high cycle fatigue strength were categorized. We can then put the structural information of the different specimens into a specific form that can be used in machine learning methods. The motivation of carrying out our study in this way is to design a tool that can relate processing parameters to the structure to predict its properties, which in this case is the material's high cycle fatigue. This model can then be used by engineers for a variety of different applications, including design specifications, process optimization, quality assurance, and certification, etc. So this presentation will first cover how we acquire the process structure high cycle fatigue strength data on our additively manufactured Inconel 65 parts, and then I'm going to analyze the data from a damage tolerant design point of view. Another section of this research, as we indicated, was to analyze collected data from a data-driven method that would typically be used in machine learning methods. However, in the interest of time and the scope of this presentation, I will only analyze the data from a damage tolerant design point of view, since that's where my responsibilities really lie. And I will briefly discuss the preliminary results that we had from the machine learning methods. So in this project, we made 11 different additively manufactured builds using the same build plate layout as you can see on the image on the left. It consisted of several different specimen types, including different high cycle fatigue specimens in the dog bone samples, and the round bars were used as tensile specimens. Specimens I was specifically observing were the small high cycle fatigue specimens, both in the Z and XY direction. And I will also discuss the microstructural specimens whose dimensions can be seen on the right, since they were useful in characterizing properties such as the porosity. So to be able to test our specimens, our experiment was designed to collect data on the high cycle fatigue strength by using the step test method. Essentially, this is where we had different test specimens that were manufactured by different set processing parameters. We would subject the specimens to a cyclic load for 2 million cycles. If the test specimen did not fail in this first 2 million cycles, we would increase the cyclic load in the next step and subject it to another 2 million cycles. This would continue on until the test specimen failed. This method was specifically useful for determining fatigue strength for one-of-a-kind specimens. These tests were conducted on uniaxial servo-hydraulic test frames, Instron test frames, and using the parameters chosen on the Instron machine, we could conduct around 1 step per day. Essentially, we would conduct a test. If the test specimen didn't fail, we would conduct the next step the next day until. And on the right over here, we can see the decision tree for choosing the initial stress we would apply onto the material from the Instron frame. Essentially, we would initialize tests based on a percentage of what we thought their fatigue strength would be, and we would continue running tests like this until it failed. So the specific details of the build parameters are shown here on this slide. We have 11 different builds, as I mentioned, and we mainly varied the velocity and half spacing. We also subjected the specimens to a high isostatic press, also known as hipping, which is where essentially we put the specimen into a high isostatic pressure chamber and subject it to high temperature inert gas. The purpose of doing this is to try and reduce the internal porosity and lack of fusion defects inside the material as much as we can. The fixed parameters we can see are also listed on the right, and were constant through each build. Ultimately, as shown on the equation of volumetric energy density, as you can see, as shown on the right, the two varying build parameters, half spacing and laser velocity, alter the energy density. So from observing the microstructural samples from the build plates, as we have highlighted on the right, we can see the variations observed in the microstructure optically without any edging. As we can see, porosity is a significant feature in these microstructures, and in many builds, hipping tended to reduce the porosity, but not in all of them. And in some of them, it didn't have any significant effect at all, as you can see in builds 7, 8, and 9. Even with these porosity defects and flaws, we will see later that yield strengths are actually still reasonable, even though there is still a clear reduction in fatigue strengths with increased material porosity. So we quantify the porosity using the images on the previous slide. These are the results of the quantified porosity as a porosity volume fraction on the y-axis and the build number and specimen numbers on the x-axis. We've made sure to highlight the pre-hipped samples as well to observe the difference hipping made on the porosity. By and large, if the porosity volume fraction is good, we characterize it to be less than 1%. And if the porosity is not good, it's usually much higher than that, around 3 to 5%. We also used a roll plate specimen that was not additively manufactured as a benchmark to compare our 3D samples. As we will see, when it comes to fatigue strength, the roll plate has the highest fatigue strength because it contains almost no defects. And we can see, however, when it comes to tensile strength, it appears that porosity actually doesn't have much of an effect on tensile strength. And you can see this in the small graph on the right, indicating the tensile strengths of the rolled plate in blue and the other builds in orange. And you can see that the tensile strength is pretty similar for all these builds, even though the porosity of some are very different. So here's a summary of the high cycle fatigue results. First, we can look at just the Z direction, both as is and polished. Polished means that the specimens were machined after the HIP process to remove any surface effects. In this case, the driver for fatigue should be related to the porosity or microstructure of the samples and not the surface. Interestingly, as we can see, Polishing appears to have better or have higher fatigue strengths than the as-is condition, suggesting that surface roughness does indeed play a role in the fatigue. Another interesting observation, as we can see on build 4, for example, I've highlighted that over here, was that there was significantly reduced fatigue strength for both the as-is and polished set. If we look at the specimen as analyzed under a scanning electron microscope, we can see that there's a large lack of fusion defects that contributed to the crack formation, which is much larger than the ones we observed in builds 1 to 3, for example. We will see that in many cases, this radical reduction in fatigue strength appears to be mostly due to fusion-type defects being present. So here's a comparison of the high cycle fatigue results in the Z orientation and XY orientation for specimens that were not polished. As we can see, it's quite clear that the fatigue strengths of all the XY specimens in gray are much smaller than the specimens built in the Z direction in all cases. The reason for this was learned by observing different fracture surfaces of specimens built in the XY direction. We found that the majority of the cracks, if not all of them, appear to form on the narrow edge at the bottom of the build. And we can attribute this to build supports that were placed at the bottom of the narrow edge of the builds, which kind of changed the way these samples were built, and it basically introduced the lack of fusion defects just because the build supports were over there. And you can see on the part of the narrow edge is where the crack began to form. If we look at the scale of the image, it's around 300 microns. And that's a relatively large defect in comparison to the ones we'll see in the Z direction, which are mostly around 50 microns. The Z-oriented specimens didn't have these features, and we can see that this is what contributed to the lower fatigue strengths in the XY build. This brings to light an important factor that may be useful for future designers, that when designing additively manufactured component that's going to be subjected to high cycle fatigue, it's quite critical to not put the highly stressed region where the build supports are going to be located, because you will have these lack of fusion. So in an attempt to make sense of our data, we first used a damage tolerant design point of view, where we underwent simulations to cracks at different locations. In the middle here, we can see where we consider these crack possibilities for our simulations. A crack forming on the narrow edge, the wide edge, offset from the middle, and then a crack forming at the corner. Using the software NASGRO, which uses material data from Inconel 625 to create a simulation of such an event with finite element analysis methods and a fatigue crack growth rate model. The figure on the right shows the results, which considered initial crack sizes from 10 microns to 500 microns. The 10 microns pretty much correspond to the fatigue limit that was observed in the rolled plate, and we will subsequently see the results from additively manufactured builds on later slides. One note here is that the difference between where the crack starts didn't really change the SN curve significantly, but in all cases, the simulation data shows the cracks starting at the wide edge appear to have slightly lower fatigue. And so the wide edge of the SN curves will be displayed on this slide. So here we can see the comparison of the SN curves, just the wide edge for all different crack starting sizes denoted here on the right-hand side for the 4 different conditions. The left 2 graphs show the Z-oriented builds in the as-is and polished conditions, and the right 2 graphs show the XY-oriented builds in the as-is and polished conditions as well. The way we grouped our data is by the mean porosity in the post-hip microstructural samples, which was broken down, as you can see on the legend at the bottom. Every symbol that's a black square were the quote-unquote good samples, which had a porosity of less than 1%. The red solid circles were the next specs with 1 to 2%, and the open samples were some of the worst. So looking at the plots, we can see that when the porosity is low, the samples have much higher fatigue strengths as we would expect, and we can see that for the as-is Z example, that they all lie above the initial flaw size. If you look at the polished data, the fatigue strength is even higher, showing that there is an influence of surface roughness on the high cycle fatigue, as we observed earlier as well. The XY-oriented specimens exhibit lower fatigue strengths, as we saw in the bar chart, and as we know, they tend to fall between 500 to 200 micron curves, even for the low mean porosity. The one thing about mean porosity, however, is that it doesn't seem to capture all the porosity information. For example, the mean porosity for a Z and XY sample may be the same. However, a lot of porosity in the XY sample may be located in the narrow edge of the build, where the build supports were, which could cause lower fatigue strength as we observed. There's also one outlier here, right over there. And what we found was that there was a large area of lack fusion type corner. And you can see that in the scale over here being 1 millimeter. So this is very consistent with where it's located to what is predicted by the damage tolerance. So the plots on this slide look at the data in a very slightly different way. Instead of scaling it using the porosity in the hipped microstructural samples, we use the porosities in the pre-hipped microstructural samples. This means that the builds can be examined immediately without any post-processing, and this was done in order to hopefully give us an indication on how to decide whether the build is good enough before going through with the post-process hipping. The scaling here is also different, where the best case is under 3% mean porosity. The second best is between 3 to 5%, and so on, as you can see on the legend below. It appears to show that if you only accept builds that have less than 3% mean porosity, it would suggest that after hipping, the samples, you would have SN curves that would meet the equivalent initial flaw sizes of about 50 microns in the Z-oriented and about 200 microns in the XY-oriented. With the 200 microns again coming again because of the build support. We can hypothesize that if we didn't have the build supports or machined the material near the narrow edge where the build supports were even more, the XY specimens may have been more comparable to the Z-oriented. So here we can present our data in the Kitagawa-Takahashi diagram, which displays the flaw size on the x-axis and the stress range that causes failure in the material on the y-axis. This shows our NASGRO simulation analysis, as well as our baseline plate data for 10 million cycles. The fatigue limit is noted here in the horizontal line on the left for the flat plate. And you can see the curved line shows our NASGRO data. This is useful because it gives us balance on the different stress ranges that can be applied to the material before failure occurs. This graph essentially shows that if a specimen is underneath the curve, you're safe. However, the closer we get to the limits, the lower our factor of safety. And one note is that we can see that the transition flaw size is about 20 microns, which is consistent with what we were observing in the microscopy observations. So now I would like to turn our attention very briefly to the results from the data-driven approach for machine learning methods. Here we use the structure as a source of information that will link the process, structure, and high cycle fatigue strength. We can see comparison of the predicted fatigue strength between the build orientation, both Z-oriented and XY-oriented, generated through machine learning methods. It tended to show that the Z-oriented had higher fatigue strengths, which we observed, and it also showed that the better fatigue strengths are at the bottom left of the graphs, in yellow, with smaller hat spacings and scanning speed, which correlates to higher energy densities, which is what we expect and observed in our data as well. So here are just some closing remarks and conclusions. Regarding observations from the additive manufacturing process, we showed that there are considerable structure and property differences between machines with the same processing conditions. We saw that most internal defects were lack of fusion type defects, with volumetric energy densities that was a bit too low in those samples. And finally, we also saw that the hot isostatic press was not a cure-all for all post-processing. Regarding the high cycle fatigue behavior, we found that the high cycle fatigue is sensitive to process defects. We saw that if the porosity is not extreme, the fatigue strength increases when the surfaces are polished, suggesting that surface roughness on the material does play a pretty large role. And finally, we also saw that the fatigue strengths of the Z-oriented builds are generally greater than the XY-oriented builds, which is attributed to the fact that cracks often form on the narrow edge connected to the build plates via build supports. Regarding our advances in life prediction and modeling, we saw that the damage-tolerant design methodology, coupled with our specimens, has utility, and it does show promise. However, we still need to continue generating more data and updating this for the completion of the study. Finally, I would like to thank Dr. New. Working in his project has been an absolute pleasure and a great learning experience. And I would also like to thank Dr. Tim Lewin for allowing me to be registered under him, and the other graduate students who began this project before I joined. Thank you for listening, and I'll be happy to take any questions.
For the room, any questions?
Yeah.
Can you go to the slide that
This one?
Yeah. So, okay, so there's 11 different ways, 11 different types of
Yes.
specimens that you tested?
Yeah. So essentially, each of these 11 had different things that were varied. And we did also vary the heat treat cycle treatment. But what we saw is that this really didn't have any effects because of the hipping, the high stress. So essentially, you can just kind of ignore this column. This is just the machine that was used to 3D print it.
Yeah.
And this is just the energy density equation, which is the function of these.
So you, like, for each of these 11, you did it once where it was printed in the XY direction. How many of each specimen did you test?
So you can see that over. You can see that over here. So for the small samples, we had 6 for the XY and 6 for the.
Oh, okay.
Any other questions?
So, a couple things. So, can you look at the porosity when you showed the different porosities? You made an argument. No, backwards. You made an argument that porosity volume fraction wasn't really important when you compared the tensile strength. I guess it depends on how much, right? If you're talking about a 10 or 15% effect on the porosity, it seems like that you could have said, okay, if the porosity is over 4%, we have a problem.
Yeah, so actually that is kind of how we ended up characterizing it. If you saw in this thingy over here. So we did say that we kind of characterized a good porosity level to be less than 1%. And then.
But was that based on this tensile strength or was that based on fracture?
That was based on fracture. That had nothing to do with tensile strength.
That's what I was saying. So tensile strength, it seemed like there is a difference based on porosity.
Yes, there is.
It's just not 50%, but it's a thing. And the second question relates to a couple different things you said. There always seems to be a few high porosity cases that do really well, like in the Z-oriented polished. You can see that little red square that sits up there, and the same thing happens in the Z-oriented pre-Hitler.
Yeah.
There's some, I expect there's a lot of high porosities that do really well. Can you comment on why that is? And what's so special about those cases?
So I think it has a lot to do with where the porosity is located and how distributed porosity is. So for example, to go back to the XY builds, you saw that if a lot of the porosity was in the narrow edge of the build, it just ended to break a lot easier, even if the mean porosity around the same, or like it still had a pretty good mean porosity. So I think a lot of it also had to do with the distribution of porosity, which is also some. I didn't go over this in my presentation, but that is something we tried to characterize in machine learning methods as well. There was like some two-spatial statistical quantification of porosity distribution probabilities that works, but that wasn't really something I was involved in.
So you're creating this like machine learning program to like figure out what's the best way to manufacture parts for this.
Essentially.
Is there like, and it's like limited to the whole 3D realm that you went over?
Yeah. So this is all these builds were 3D printed.
Yeah. Is there any? What was the? Did you before this the project looking at other manufacturing techniques? These parts?
To be honest, I'm not too sure. I joined this project a little later, but I do believe that there was some research done on that. I think there are some advantages of laser powder bed fusion, particularly that it might just be easier to do. It's a little cheaper because you can just do it with this powder. So yeah, I think that's
High temperature materials too.
Yes.
Fusing requires high temperature. Were you asking about different additive manufacturing approaches, or were you talking about?
No, just like you're looking at the additive manufacturing, but you look at like other ways to manufacture, like just like casting or anything like that.
No. This was just based on.
I would add probably we know a lot about traditional casting strengths and heat strength like that. The question is here: can you build parts that would be very difficult to make in other ways?
Yeah.
And how would you characterize? Could you answer one more question at least, which is back to the machine learning?
Uh-huh.
You showed the results of the machine learning interpretation. Was that, and you said it compared well to your results, was that learning based on your full data set? What part of your data set was used to produce this machine learning number?
So actually, this machine learning was done quite a while ago when we only had a little bit of data. It hasn't been updated yet with a lot of the new data that we've been using. So this is still like very preliminary. I wouldn't 100% agree.
But when you said agrees with your data, is it just a fit to your data, machine learning fit to your data, or is it a prediction where you've gone off into a new space and done something new and compared?
So I think it is a prediction, just based on what I know about how they've been doing this machine learning stuff. They've been doing a lot of analysis on the probabilities that they gathered from data.
From the same data that you're showing us?
Yes.
So your data is used to derive this?
Yes, that makes sense.
Anything else from online? Well, if not, let's thank our speakers, both of them. Look forward to another